Welcome, everyone present here. Team GDSC, in association with Skepsis, has organized for the ML and TensorFlow Bootcamp 2023. So, whether you are a beginner looking to explore the world of machine learning, experienced practitioner seeking to enhance your skill, Machine Learning and TensorFlow Bootcamp offers a unique opportunity to expand your knowledge and expertise. I welcome you all to embark on this incredible journey with us. Together, let us unravel the mysteries of machine learning and unlock its vast potential. Without much ado, I would like to call upon stage Vasim Rajak to introduce the bootcamp.
Hello, everyone. Welcome to Machine Learning and TensorFlow Bootcamp. So, let me give you a brief introduction about what you need to expect and what you're going to experience. So, is the screen shared? Uh, Someone just informed me.
Yes, yes.
Okay. So, welcome everyone. This is Machine Learning and TensorFlow Bootcamp organized by Skepsis in collaboration with GDSC SNE. So this is going to be a 3-week bootcamp. And after a lot of thoughts and discussion, we have come up with this because topics like web dev and UI UX have been taught by other clubs. This topic was remaining and people need to know about this actually. So as I said, you will need you will know that what you need to expect from this bootcamp and what you're going to experience. So let me give you a brief introduction. So you're going to explore different aspect of machine learning. Machine learning is a term that we come across pretty often, but we don't really know what it is until we work with it. And in this bootcamp, you're going to work with machine learning pretty deeply. So get ready, engage in multiple hands-on projects. So multiple as in, yes, you want to engage in three hands-on projects. So, and you're going to get evaluated based on that and you will know your progress. In the finale, you will be rewarded. So yeah, a lot of things are going to happen. Receive guidance from mentors. We have expert mentors. We have brought expert mentors for you who are going to guide you. So let's go to the next slide and what you need to know. So of course, machine learning is not a small topic. You need some prerequisites to start with machine learning. You need to know basics of Python, basics of data structure in Python, NumPy and Pandas. So if you are thinking you don't really know these, then don't worry. In GDSC SNU's YouTube channel, we have uploaded these videos, basics of Python, data structure in Python, and NumPy and Pandas. So you will get the link in the group description. Uh, it is mentioned the playlist link. So if you haven't done it yet, you can do it. It's still there. So mentors, there will be two type of mentors in this process. Like it is a 3-month um, bootcamp. So there will be external mentors and there will be internal mentors. External mentors will help you understand the basic concepts, whereas internal mentors will help you build projects based on those basic concepts. So, yep, there will be it will be 3 weeks. So the topics of 3 weeks boot camps are introduction to machine learning, introduction to image processing, and TensorFlow and model deploying. So in this 3 week, there will be 3 classes of the external mentors, which will be on every Saturday, which is July 15th, July 22nd, and July 29th. And every week on Monday and Wednesday, there will be internal mentors sessions, which will be July 17th, July 19th, July 24th, July 26th, 31st July, and 2nd August. And the finale will be on 4th August, which will be offline on SNU Seminar Hall from 3 to 5 p.m. Now let's talk about the projects you're going to do. So as I have already mentioned that the first week's topic will be Introduction to Machine Learning. So based on that, you will be given a project on linear regression. Linear regression, like a project will be linear regression model to predict housing prices. In the second week, the topic is Introduction to Image Processing. So the project will be OpenCV model to detect edges. Edges as in like, yep, edges. And in third week, the topic will be TensorFlow and model deploy, where you will just deploy a TensorFlow model actually. So, and this is all that I need to tell you about this bootcamp. There is a lot of things you will experience. Uh, wish you best of luck. So, yep, I hope you all are well informed about what is going to happen and you're going to do it great. So, yep, passing you on Ankanadi.
Without further ado, I would like to call Mr. Aan Patel to continue with his presentation.
All right. Yeah. Hi, everyone. And thanks, Kna and Wasim, for the warm introduction. Yeah. So, hope you're all as excited as I am to kick off this machine learning bootcamp. I'd like to first thank all of you for being here and thank SNU and everybody in the organizer team for inviting me here. So, yeah, let's get started. Let me screen share. All right. First off, just let me know if you can read the screen properly and if you see everything um, in a good fashion. Um, okay. Silence is a yes. All right. So yeah, once again, welcome to this intro to machine learning session. So today, so let me give a brief introduction of myself. So I usually dabble with software engineering. I'm a software engineer by profession. I work with mostly JavaScript tools, but outside of work, I try to explore machine learning and Python a bit here and there. And so what you're going to get today is a broad overview of machine learning from the perspective of a software engineer, which means a lot of the focus would be on grasping the higher level details and how to get to a solution to solve problems, right? You will learn about all the concepts, or I'd say not all, but most of the concepts involved with training machine learning models. You will build some fundamentals and you will get a basic pathway to kind of go deeper into machine learning. So there's a lot to unpack here. And there are lots of domains within machine learning as well. So this would probably just be like a broad overview. Okay, with that out of the way, let's get started. So I want to make this interactive. So feel free to unmute yourself when I ask questions and just try to answer, try to be interactive, and let's make it fun. So before we get started, I hope you didn't start reading all of this. I want to get your perspective of what you think machine learning is about. You can raise your hand and then, because I guess there would be multiple people, I can pick your name and then you can unmute and give your answer. Okay, so to you, what does machine learning mean? It can be, it can mean different things from different perspectives. So, all right, I see a hand from Praneeth.
I think it is about pattern recognition.
Okay, yeah, that makes sense. You can recognize patterns using by training models using machine learning. Um, what do others think? What is machine learning about? Okay, I see a hand from Aditya.
Good evening, sir. So,
Yep.
so according to me, machine learning is basically a tool which we use to make an AI think like a human, and like how a kid, you know, starts learning through pattern recognition, like in alphabets and all. So, machine learning is basically how we teach a kid. So here, in this
So,
scenario, kid would be a machine like a computer. So that's
right.
my
So
perspective for it.
essentially, you mean to say that machine learning is machines learning to do things by themselves, like humans. I see a hand from Jamilur. I don't think I spelled your name right, but Jamilur?
Yeah, hello. Good afternoon. Am I audible?
Yep.
Yeah. For me, machine learning, it is a subset of AI that basically focuses on developing the algos and statistical model so that the computer can predict and make the decision on based on the data. For me, that's it.
Also a pretty good definition. Anyone else? I see Jishnu.
Hello, sir.
Yep.
So, according to me, machine learning is making a machine learn by doing things.
Yeah, that also makes sense, right? So you teach a machine how to perform certain tasks, and it learns to do those by itself without explicitly telling it to do those, perform those exact steps to solve the task. Okay, so those were really good definitions. And I guess you're already prepared and you already have a good introduction to machine learning. So kudos to that. So let's look at the definitions of some of the big giants in the field. You might have come across the names Tom Mitchell or Arthur Samuel. They are pretty renowned researchers who have contributed a lot to this field. So let's look at what Tom's definition is. So Tom says that machine learning is about, well, he says a computer program is said to learn from experience um, on a task for a task T with performance measure P if its performance improves with experience, right? So that's Tom's definition. And there's also another definition from Arthur Samuel, which states that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. So, what that means is you don't specifically provide the exact steps to a computer to solve a problem. Instead, you make it learn to program itself to solve that problem, right? And you might think, well, I write code in languages, high level languages like Python, C, C++, and many more. Well, a program, well, ChatGPT can do it now, but in general, a computer program you can't really make it, you know, directly write code. Then why is it that we say that machine learning is basically building programs that program themselves? It's because they program themselves by setting parameters. And we'll get into more depth later on. But let's move on. I think we have a good idea about the definition or about what exactly machine learning means, right? I'd pause here for a moment and look for questions people might have. Um, if you are still trying to grapple with what the heck is machine learning, just raise your hand and unmute and let me know what's kind of uh, stuck in your head. Um, okay, and pause for like 15 seconds. Okay, I have Jamilur.
Yeah, this time you pronounce it right. Yeah, the thing is that machine learning basically follows the pattern. So nowadays we can see that ChatGPT and so many AI models, they are following patterns so quickly and they are making the prediction more precise and more quick. Like now we can see like Bird is doing right now. So nowadays the pattern recognition is changed, or like the AI is more advanced for that they are recognizing better what is going on, what is going the background here right now.
So in the background, actually, these models they are not one model per se, but they are a collection of different models, and they are wired together in a kind of a pipeline, right? So you have these huge models that are trained on um, tons of data from the internet, and they have not not millions or billions, but hundreds of billions of parameters, which let them imbibe within them the state of the real world, right? So these models have gotten so big that they can now sufficiently represent the world, right? The concept of a lot of different concepts in them, right? So that is why they are getting pretty good at doing things or tasks that humans are really good at. So we'll look at what parameters mean and what um, model size means as we go ahead. Things will get clearer. um, are there any other questions? And did I answer your question, Jamil?
Yeah, thanks.
All right, looks like that is all. And let's move ahead. So let's see what these programs that can learn to program themselves mean for you as a developer, um, right? What can you do with this ability of computers to program themselves, right? So one of the advantages you get if you use this concept of machine learning is that it lets you reduce the time you might have to spend programming, right? Writing code. And so why does it reduce time? Well, imagine you are trying to build a program that looks at MRI images, MRI scans, to figure out if the patient has cancer or not, right? Now you can write a program. An image is basically a set of pixels, right? Each pixel has color and intensity, and so you could go pixel by pixel and figure out some weird if then else logic. I don't know how I don't know if anyone has ever tried to do that on an image, but you could write a huge program and hard code all the decisions to figure out if an image is that of a cancer patient or not. But I think that would be a vain task. You would fail terribly at it, and you would have spent years and years writing those conditionals, right? But machine learning gives you an alternative approach that lets the machine handle tuning those parameters and figure out the patterns in the data to then program itself to be able to perform that task. So you could do the same thing of recognizing cancer given an MRI scan, within a couple hours using the power of machine learning, right? Um, okay, so it's basically letting the computer take care of setting the knobs, right? You have a complex model of something of we'll talk about what models are, but basically you can think of machine learning as you have a big system and then you ask the computer to fine tune the knobs to make the system perform the task that you are trying to make it be good at, right? The next benefit from machine learning or of using machine learning is that you can perform transfer learning. You can customize logic for different use cases or user groups. What does that mean, really? So here's an example. There are models in machine learning that will let you um, take any random image and then find items in those images and label them, right? But then these models are trained on a lot of data. Another example would be the GPT models that back ChatGPT, right? They are huge, and it's probably really costly to even implement them. And so um, developers like us don't have enough resources to train such huge models from scratch, but those models also imbibe in them a representation of the real world, which you can leverage to solve your own specific problems. And that is exactly what transfer learning allows you to do. You take a large model that is trained on some general task and specialize it to do specific tasks. Like, for example, here, there was a model, ImageNet Cafe Alex, that was trained on the ImageNet dataset. ImageNet is a dataset of tons of images, with each image having a set of labeled rectangles telling the computer where exactly an item is and what the name of that item in the image is, right? So they took this ImageNet general model that can tell you about items in any image, and they tuned it. They used the concept of transfer learning to use those powers of being able to tell what is in an image to to train it then on images of deceased kidneys and figure out if the patient has chronic kidney disease. So that is one example of using transfer learning. There are many more in different domains, like recognizing voices. So a lot of the voice assistants that you might have used, like Siri, Alexa, Google Assistant, they utilize transfer learning. There are also recommendation systems. Basically, you might have seen apps like Amazon recommend you things based on what you have already bought. Well, they also, on the back end, use huge models that are trained on tons of data from millions of customers to then give you recommendations just for your specific user, right? And so they can provide you personalized recommendations. Last but not least, you can do text classification or analyze the emotions within text using some of the large language models. So there are models that, given some text, they will give you a vector. Is everyone on this call familiar with the basic mathematical concepts like vectors and matrices? If not, uh, you can type "not familiar" in the chat. I'll wait for a few seconds. Um, Okay, looks like people are familiar. So I will use these math terms freely. Okay, um, thanks everyone. Okay, so now you have a basic idea of the two benefits that we've discussed so far of using the concept of machine learning, right? First is decreases programming time. Second is it lets you use these huge models for your own specific tasks and utilize the abilities of those huge models and take advantage of them for your own specific smaller tasks, right? Um, and the last but not least, and all of these benefits are kind of entangled so with each other. So there's an overlap between all of these benefits, but it lets you solve complex problems as well, right? So if you thought about 2.1 decrease programming time, like it's really talking about the complexity involved in writing long programs to perform decisions or interpret the data that's passed to your program, right? So what machine learning lets you do is defer that to the computer. And so here are some examples. Imagine writing a program that looks at an image and then infers the names of items that are present in it. The cafe ImageNet model that we looked at above did exactly that, right? But how would you do that if you were just given a Python REPL shell and just asked to write a Python program to do it without using machine learning? Would be, believe me, it would be an uphill task. Another example is listening to audio, providing transcripts of that audio, or identify the emotion of the speaker. Does the audio seem like someone's happy or sad? Um, Look at images of plants and infer if the plant has some disease. This has applications in farming. It helps. It even helps large scale farmings in a lot of modern farms. And you can also do things like reading natural language and see what emotions it portrays. And here's an example of another machine learning solution and how it works. So basically, through this example, let's start talking about some of the terminology involved with machine learning. But I'll just pause for a bit here and see if there's any questions. Okay, there's Jamilur again. Yep.
Yeah, I heard about that image processing and NLP and natural language processing thing. But recently, in fraud detection, uh, so many e-commerce websites like Amazon, Flipkart, so many companies are using fraud detection system. So in email, basically what happens, if they use the previous data and by using their pattern, they predict the thing there that can be a fraud or not. But what if the new kind of fraud happen? How can the email will detect that?
So basically, these fraud detection systems work on the concept of outlier detection. So as you mentioned, you got it exactly right. It detects if there is an anomaly in the data coming in from the pipeline, right? So it has a representation built in that lets it figure out if something is a fraud. If, let's say, we are talking about transactions, then the model can predict if with a certain accuracy, and there's always probabilities involved with these models. So you can never say for sure that it will catch all outliers or anomalies in your data. But what these models do is they have in them imbibed the pattern of what it looks like, what the outlier looks like, and what a normal data point looks like. And once they have that embedded in them, if any new data point comes in, they run inference on it and give you a probabilistic estimate of what they think this data point, what category it belongs to, right? And so there is a chance that the model can be wrong, and there is a chance that the model can be right. As machine learning engineers, it's our task to try and make sure that it gets it right most of the time. Right? Did I answer your question?
Yeah, I got it. Thank you.
Thanks. Um, all right. So if there are no more questions, I'll move ahead with some of the basic terminology. So let's take an example of a program. We're trying to write a program that identifies flowers, right? How would you do that? And how could a program detect whether a given image is that of a flower or not? We can basically, in machine learning, what you can do is provide the system data and train the system on that data so that it learns those patterns and remembers them, so that the next time it sees a new input pattern, it could be that that input was never seen before, it can still provide you with an output, right? And in order to do that, we we need to have a kind of a set of terminologies and a kind of a framework around how we shape our problems. So in machine learning, um, when you feed a model some data to train it, to make it learn those patterns in your data, you call that data examples. So data is essentially a set of examples, and you train your model on those examples. An example consists of an input, which here is represented as X in boldface. So um, an, ex- an example input can be multiple numbers or a single number. And a label is, again, it is usually also multiple numbers or a single number. And so usually machine learning models, what they do is they get an input, right? And they try to predict its label. Um, and the way they do it is by looking at the data you trained it with, learning those patterns, and then applying those patterns on any new input they see to give you the implied label for that entry. So here's an example of machine learning. There are two different approaches. We will talk about them later on, but consider this example of trying to predict what type of iris flower. So these purple flowers are called iris flowers, and there are three different kinds. There's iris setosa, there's iris versicolor, and there's iris virginica. And of these three, given some numbers, right, about how big their petal is and what the dimensions of its sepal are, and you were trying to predict what species of flower, what species of iris flower this particular sample belongs to. Um, can okay, I guess it's on the board here, but um, can anyone tell me what a feature is in this case? I wish I can hide the table on the side, but being honest to yourself, don't look at the table and try to tell me what a feature is. What do you think a feature is, and what is a label? Feel free to raise your hand and and kind of bounce ideas around what you think is a feature. Okay, Jamilur again. Okay.
Yeah, yeah. I think in this case, it is considering the width and the length of the petal and the sepal, so that it can detect the other things properly.
Yep, you nailed it. Cool. If you guys are in a room and there's like candies around, please throw a few at Jamilur. Okay.
Thanks.
So yeah, so now you have a basic idea um, of what a data set looks like when you're trying to train a machine learning model, trying to make it learn about the patterns in your data, right? These are the basic terms that you need to be aware of, basically features and labels. Most of the time, you'll see that data would exist in the form of a table like this one. So if your problem task was to identify the kind of flower, eh, like the kind of flower that is being passed in as input is, then you look at all of these properties and perform certain calculations to predict which species it belongs to, right? So you take the features as input to predict your labels. That's in a sense um, the next thing that we are going to look at, which is supervised machine learning. So in machine learning, there are two main approaches um, involved. So first one is supervised learning, and the other one is unsupervised learning. Does anyone have an idea about these two concepts? Okay, Jamilur again.
My question is different. I think there is another one, right? Like in reinforcement learning, if I'm not wrong.
Yes, there is also a concept. Yes, you are correct. There is reinforcement learning, but you can think of it as a subset of supervised learning because at the end of the day, you are trying to minimize loss and trying to make the agent perform a certain task. But again, there's also an overlap between the fields of AI and machine learning. And so reinforcement learning kind of lies in between the two.
Okay.
All right. Are there any other questions? Okay. All right. So yeah, let's move on and talk about supervised and unsupervised learning. Um, the bulk of our time through this session and perhaps the next in this week, because I saw this week you guys are doing linear regression, would be spent in on supervised learning, right? So let's take a look at what supervised learning is about. So it's really what we just looked at. It's algorithms that can learn from labeled examples, right? So where each example that is passed to the model while you train it, it consists of an input, which could be a set of features and a label, right? Which is represented as Y usually. And so the program then learns how to make, how to infer the label value Y given the input values X, input features X. So basically you feed it a bunch of data, right? You feed it a set of features and your label, and then it starts to figure out how it's going to give you the correct species in this case, given the set of features about the sepals and petals, right? Um, Here is another example data set. And I'd like you guys to answer this one. Someone other than Jamilur, figure out If the problem was to predict the selling price of a home, so this is the data of homes that were sold recently. And we have four columns, right? First one was what the house was sold at. The second one is the square footage or the size of the house. The third column is the number of bedrooms in that house. And the fourth one is how old that house is. If you were told, you were given this data and you were asked to write a program that predicts the selling price given the square footage and number of bedrooms, what would be your features and what would be your labels in this case? I see a fresh hand. It's Rima.
Okay, so here the label will be the selling price and the features are square footage, bedrooms, and age.
That's absolutely right. For this particular problem, we are trying to solve for the selling price, predicting the selling price given the square footage and number of bedrooms. So if you were explicitly asked to train a model to predict something given certain things, you should treat only those things that your model will be passed when running inference, right? So in this case, even though we have age as a column in the data set, it's really not that useful to us because age is not one of the inputs that you will be getting when you try to run inference using your model, right? So your expectation for the model here is to provide it the square footage of the house and the number of bedrooms, and then you're trying to ask it to provide you with a selling price, right? Um, so the age column essentially is not a feature for this machine learning. But you're right, the selling price is the label. And the two features we are going to be using for training this model would be the bedrooms and the square footage. Um, all right. So there are a lot of examples of different kinds of machine learning models that you can train. And you'll see as you try and explore the data sets that we are going to look at today, how you can figure out which model works best, right? Sometimes picking larger models, it might be counterintuitive, but if you pick a very complex model, sometimes it can ruin your performance and the model really doesn't do well at a task. So there needs to be a really good balance and an organized way for selecting which model you are going to train. Um, so here are some examples of supervised machine learning models. The first one is the one you're going to be probably looking at for this entire week. It is linear regression. And does anyone have an idea about what the word regression mean? Okay. So let me explain the term regression and what it means. Essentially, with machine learning models, you can either make them classify certain things, right? Or you can make them provide real valued outputs. For instance, in the problem above, you can provide your machine learning model that you might have trained to solve for this problem statement, you can provide any real value for square footage, any integer for bedrooms, and you would expect any real valued price as the output, right? So when a model is able to, when a model's prediction is a real number, you can think of it as a regression model. And when it is, when the output is restricted to certain number of distinct unique values, you can think of it as a classifier model. And so the basic distinction between regression and classification is that a regression model will always give you real valued outputs or predictions, and a classifier model will always give you an output from within a set of distinct items. So for example, this machine learning um, model, if it was predicting the, the species from among the three, which is Setosa, versicolor, or virginica, it will be treated as under the hood as a real, not a real number, but an integer that can take a value between 0, perhaps 1, and 2. So you can give it any label, and the model will always output one of these three, right? So you have a distinct set of possible predictions. And so that makes it a classification model. It classifies, given the information about the example, it classifies it into one of the three species, right? So that is a classifier model, a program that takes in data and then gives you what class it belongs to. To the contrary, a regression model really takes in data and then provides a predicted value for something. In this example above, it was predicting the price of a home given the square footage and the number of bedrooms in that house. Okay, so that's a bit about supervised machine learning. We will talk about neural networks, I guess, in future sessions, because I think we have about an hour to go. Let me give you an example of another machine learning algorithm different from linear regression and linear classifiers, which we will be exploring in detail soon. So there's this another kind of classifier called the k nearest neighbors classifier. And that lets you, let me see if I can move to another tab. Let's see. All right, share this tab instead. All right. So assume you have a set of data that you plotted in a 2D scatter plot, right? And now you are given a new point, a red point, and you're trying to predict where this new point that you injected belongs to. Does it belong to the orange group or does it belong to the blue, right? What this algorithm, it's called k nearest neighbors, and it is a supervised learning algorithm because it looks at each data point and its values and it remembers them. So it will look at each of these blue points and it will remember them. It will look at each of these orange points and it will remember them. And when a new point comes in, it'll look at the n, or here it's called k. So it'll look at the k is a number you can set for the algorithm. And it will look at the k nearest dots and figure out from among those k which color is a majority. And that would be the class of this new dot that you just dropped in. are there any questions about this algorithm? So it's called the k nearest neighbors algorithm. It is a supervised machine learning algorithm because you feed it both your features. So here features would be plotted as dots, and you can think of them as the x and y axes. So x and y both, well, you can say x1 and x2 um, on these axes are the features, and then you plot these examples on your scatter plot. The color is your label, right? The label for blue is class 1. The label for orange is class 2. And you drop in a point. The k nearest neighbors supervised learning algorithm will look at the k neighbors that are nearest to the point that you just dropped, and then it'll figure out um, which class the new point belongs to. And that is the prediction of your machine learning program or model, right? Okay, so are there any questions about supervised? There's a hand from Aditya and then Jamilur.
So can I say first?
Yeah, sure, go ahead.
Sir, I have a question that what if both the classes have near to same probability? That like the distance, yes, the distance between the blue and the orange is kind of the same. So which one will it prefer more? That's my question.
So the way it does the classification here is it figures out, you set a value for k, right? In this case, it's probably, let's see how many are in the circle that it draws. So I think it's 1, 2, 3, 4, 5, 6, 7. So it looks like the k value on this algorithm is 7. So you drop a point anywhere, and then it looks for the 7 points that are nearest to it. Um, how does it calculate the distance? It is the distance between points formula that it applies um, to get the distance between the dropped point and any other point that belongs already to the data set. And so to answer your question, which was what happens if um, the the data set is too crowded, then in that case, well, if you don't see a visual separation of data, then the k nearest neighbors algorithm would not do a good job. But in this case, you can clearly see, like you can see that this whole area, I hope it's also showing my mouse cursor. This whole area is full of these orange dots. And then there's this whole area to the left, to the bottom left, that's full of these blue dots. So there's a pretty good chance that if you drop a red point, which is an input, um, onto the left corner or anywhere here, it will predict it as its as class 1, right? And if you drop it up here, it should predict it as class 2, because what it's going to just do is find the 7 points that are closest to it, right? And then figure out what's the majority class among those 7 points that are nearest to it. So in this case, it's pretty clear for the model to predict what class it belongs to. But it gets hazy where it gets closer to this boundary. And so it does, there is a chance that it can classify things incorrectly. But it, in general, um, because the way this data set is shaped, this model would do a good job at it, because um, if you drop an orange, a red point, which should be belonging to an orange point, which is if you drop an input that should be belonging to class 2, chances are that it would be somewhere here and it would get it right. So I hope that answers your question. If not, if I forgot about your question, just let me know.
No, sir, that's pretty much it. Thank you.
Thanks. Right, and there's also a hand from Jamilur.
Yeah, my question was almost similar to Aditya, but mine was bit specific. The mine question was that the ML is predicting here. Is it mostly going to the taking the vote of majority vote of the closest one, or taking the average of the closest one?
It is exactly taking the vote. So it's not about averages here. There's another algorithm called the k-means algorithm, and it is an unsupervised algorithm, which we are going to look at pretty soon. And that does look at averages in a certain way. But here, what this algorithm does really is it's really a very naive algorithm. It will, if you give it 100 data points, it will literally store them in its own memory, and then it will run through each of those 100 data points. If you have worked with for loops in Python, you'd know how to run through a list of things, right? So it will do exactly that. It will run through the entire list of each and every data point against this dot and find the ones that are nearest to it, right? Um, and and then it will reduce that list to the closest seven. If the value for k here is 7, it'll reduce that list to the nearest 7 and then do a majority vote. And you can do different things to break a tie, but usually you would not need to break a tie because the number of neighbors are always picked to be odd, right? So that if there's 5 things, you can be assured that there will always be a majority. If it's even numbered, you can have, say, if you set k to 4, you can have 2 blue and 2 orange dots, and then you're done because there's no way to tell which one takes priority, right? But you can toss a coin and do some random stuff, but usually we set k to odd numbered values, and that's how it works. I see a hand from. Did I answer your question, Jamilur?
Yeah, yeah, I
Sure.
got it. Thank you.
Okay, thanks. This Chandri.
Yes, sir. Am I audible?
Yep.
Okay. So is this how Google Maps work? Like how they identify the places nearby? Is this how they work? This method?
Is a different kind of application. They do
Okay.
use machine learning for certain tasks like satellite. They analyze satellite images. They analyze how fast people are moving on their routes, which they might have configured for navigating. So they figure out how long it would take you to get from point A to point B. But this is more of a classification algorithm, and it doesn't have to do anything with navigating from one place to the other. So Google Maps is basically a big software that looks at your location and then drops you on a map and then lets you go from point A to point B. Uh, but it might be using this algorithm for something um, under the hood, perhaps figuring out what kind of restaurants you might like, right? You have a feature set that represents the kind of things you might like. It might be able to run clustering algorithm, uh, classification algorithm to figure out what kind of food you might like, right?
Matches with like the example sets we have given in this process and then identifies particular restaurant, like you said.
Yeah. So if you were trying to pick, I guess you can have, for example, let's say you have a feature called age. Let's say this was a plot of restaurants, and like restaurants that people go to, each dot on this scatter plot would then represent a person whose choice might be to go to a pizza place, let's say blue dot is a person who's likely to go to a pizza place, and an orange dot is someone who's going to tend to go to a more traditional place. Okay, so let's say x axis is a feature that's the age, and the y axis, um, let's see what we can pick as another feature here. Um, if anyone has suggestions for this mind example that we are running, feel free to type it down or just unmute and let us know. If let's say y was some other feature, um, even still, you can see as x increases, there's a greater likelihood that the person would tend to the more traditional. So that could be a data set that you can drop your data point on and then see what the model predicts you might like to go out for a bite.
The orange dot is nearer, so it's like a class 2 situation, right? For this example that you have shown here.
Yes. So this is exactly a classification situation where you're trying to uh, make a model predict, given this data, if a new data point is provided, which class it belongs to. So that is classification.
And so I had one another question, like for the one you provided with the bedrooms one, the last one. So there we have given particular number of rooms and the square fits and accordingly the prices. So like the examples, do they need to be in a particular range or gaps, or is it like they're taking it on their own? I mean, how do we provide the examples exactly? Can they be random?
So examples usually come from recorded data, right? So you can get examples from the real world. There are lots of ways that are run. Let me see if I can pull up an example data set. Uh, Give me a second.
Sure.
All right. So here's an example of a real data set. So this comes from a 1990 United States Census, um, where it um, documents the exact location, the median age, the number of rooms, bedrooms, the value of that house, and it records that for every house in different localities. So it's a large data set that gives you a bunch of columns, right? Um, and then you can build different models on top of this to run different kinds of predictions. So if I can, this is jumping ahead a little bit, but I would want to show you the what the data set actually looks like. So let's see. Okay. So I'm printing the first 5 rows of this data set. And as you can see, this is all from the real world. So this is from that 1990 census. So some government official or a group of them recorded all of this by going all over California, and they collected all of this data. And you have it here in the form of a table, which you can then use to train different kinds of models. For example, one model you can run would be to predict the median income, right? The median income is in tens of thousands of dollars. So if you see a 1.5, it's $15,000. If you see a 3.2, it's $32,000, and so on. So given the median house value, you can try to predict the median income of that household, right? And so on and so forth. There's also some numbers around population density here. So this is an example of a real world data set. If we get the time to work on these today, we might look into these examples. But yeah, this is what a real data set looks like. Hope that answers your question. Um,
Pretty much, sir. Thank you.
Thanks. Is there anyone else? So Jamilur asks in the chat if the k nearest neighbors algorithm is mostly used in handling ties in class labels. So this algorithm is a classification algorithm, right? Um, it has nothing to do with handling ties in class labels. It only has to do with classifying. So if you visualize your data set, right, and then try to see if you are able to find different clusters that are separated enough to use an algorithm like this, to figure out whether a new data point will be a part of the same kind of visual group or the blob or not. Sometimes what you get is, let me see if I can pull up an image where it's not as clear. Let me see if I can share this tab. Okay. I'm just trying to share this image. And you can see k nearest neighbors might not do a really good job at this. It would break at these fringes because there's too many of each, and it would just be like tossing a coin because they are mixed in a large part of the scatter plot, right? As you move away, it does get better, but it's not really going to do a good job if you drop a point somewhere in the middle of the image, right? Um, so yeah, that's an example of where you might want to use something else um, and try out like different models. Okay. Moving on to the other kind of learning. So till now, all the algorithms and ways of or concepts of machines trying to predict things that we have seen have been about predicting a particular label given a set of features, like getting a set of these two features to predict this feature, right? The selling price. But there's also another class of algorithms that just take a look at your data, right? They look at your data and give you more information about your data that you can then use to do stuff with that data. These algorithms are especially useful for running business analytics. So if you are trying to see if you are running, say, a coffee shop and you're trying to see what kinds of customers are the usual attendees at your shops, um, you can use these algorithms that will let you explore your data. I see a question on the chat from Saswat Dev. Can larger values of K be taken in KNN algorithms? If you take too large of a value, you have to experiment with different values of K, but it ideally should not be larger than, I'd say 20 would still be a huge number. It also depends on how many samples you have in your data set. And if you take too large of a number, what would eventually happen is, let's say you picked 100, right? It's going to select the circle itself is going to be so large that it forgets to account for the location that the point was dropped in, right? Because you are looking at 100 points and taking a majority vote off of that, the fact that it was dropped in this area kind of gets hazier as you start increasing. Well, k cannot be 100; it can be an odd number usually, so 101. But the point still stays the same, that if you take a large k value, it's not going to give you good results because it's going to pretty much cover the entire data set. And so you lose the notion of the position of this new point that you just dropped.
So then what should be the ideal point then? Ideal value?
With machine learning, it's both a science and an art. So sometimes you just have to try out different k values.
Okay, sir.
All right. So if there are no more questions, we can again dive into unsupervised learning. All right. So where were we? Yep. So unsupervised models, as opposed to supervised learning models, really just get you a view of your own data. So, for example, you can run an unsupervised learning algorithm on this data that you already have and get it to print you a clustering of points based on, say, these two dimensions. So you can plot bedrooms against selling price, right? And then you can run an algorithm that will cluster these points for you. So it won't look at any labels. It will just go through each data point and then using an algorithm, figure out what cluster it should belong to. And it generates clusters by itself. So you just ask it to separate this data into any number of clusters as you want. And that is the K in this algorithm. So with K-means clustering, this unsupervised learning algorithm, what it will do is it will, let's say I'm trying to get a clustering of bedrooms and selling price. I'm trying to plot them, and I plot them on a chart somewhere. Let's see if I can draw. Give me a second. Okay, I'm going to open our trusty old MS Paint and see if I can give you guys an idea of what K-means does. Okay, so let me move my window a bit. See if it's sharing. All right, looks like we are sharing. So let's say we are trying to plot a data set and then trying to run K-means clustering on. So we plot data points. Let's see if I can use an airbrush. Right? So let's say we plot something like house price, that's an interesting font. Okay. So you're trying to plot house price versus bedrooms. And so bedrooms can be like 1 bedroom, 2 bedroom, 3 bedroom. Uh, let's well, this is not a really good example because it's like this. These are discrete values. let's try to use square footage. They are real number and we can plot them. So let's assume we are trying to plot square footage with house price, right? Now, you might be able to find clusters in different ways. So let's say this data set looks something like this. So okay. All right, let's assume this data set looks something like this. And now you're trying to run an unsupervised algorithm to find some insights about your data. So what this algorithm is able to do is you first assign some random points as starting points for your clusters. By visually looking at this data, you can figure out that it has 1, 2, 3, and 4 clusters. But how will a machine figure the same thing out? Well, that's where this algorithm comes in. And what it lets you do is you can drop, let's say I'm trying to mark 4 different clusters, right? So let's say I plot points like this randomly and start my algorithm. What it will do is it will calculate the, it will assign each data point that's in your scatter plot to the nearest cluster. So let's say this thing is labeled point A. And this one is the top left cluster. This is the, we can name it the middle cluster. The top right. It's the bottom. Okay, so which points do you think would probably be the closest to A? It's probably going to be this guy, probably this one is one of the closest, this one. And so the way it works is each and every point gets assigned to some cluster, right? And then what the algorithm does is figures out, so it attaches each point to one of these clusters. So imagine a line emanating from every black dot here to point A, B, C, or D, right? And then what it will do is it will move these points to the mean of this distance. So it will essentially get the center of the points that were found to be closest to it, and that will become the new cluster, right? And then you reassign, so you then have a fresh center point. Let's say you found that all of these points that I've drawn were the ones closest to point A. Which way do you think will point A move? Will it move to the top left or will it move to the right? You can raise your hand to answer. So with this algorithm, what you're trying to do essentially is first find out the nearest cluster point, and you start with random cluster points. You're trying to find which cluster point, which red dot is closest to each of the black dots. And so this black dot says hey, I'm closest to point A. This black dot also says I'm closest to point A. This one, the same. This guy, the same. This as well. And so just like that, for each data point, you will assign one of these red points as their cluster centers. And then what you do is you will move this point A to the mean or the center or the centroid of all of these points. You'll take an average and you'll move the point A, and the same for points B, C, and D, whichever points they are closest to. You'll move these to the new center. Let's say point B moves to here, right? And this point moves closer this way. This point A will move closer that way. And then you can iterate until you get to a point where there's no more change. And that's where your algorithm stops converging, is what the nomenclature declares. So, um, yes, Jamilur.
Here you are using the clustering technique. So you are using the k-mean clustering or the hierarchical clustering? Which?
This is k-means.
Oh,
So you're trying to go, you're trying to find the closest data points, and then you take or you call the red points that you dropped as the cluster centers, and you recalculate the cluster center's position by looking at all of the points that were found to be nearest to the previous cluster center. So next time, let's say you find an average, this point A moves up and it moves to somewhere here. Then if you take the clusters again, you will find that more of the top left cluster, right? More things of the top left cluster will belong to this red dot versus this one, because this thing is moving here. This thing might be moving this way because of the number of points over here that are closer to it, right? So we do a weighted average, and we move uh, we weight it by the distance. So the next centroid that gets calculated is closer to where the most dots are, right? So this red dot might move somewhere here, um, instead of going to the left, because there's more gravity towards this area because it has more closer points attached to it here. Right? So yeah, hope that answers your question.
yeah, I got.
Okay. Let me move back to the document. Okay, so uh, looks like we still have about 30 more minutes. So we'll let the last 5 minutes out for questions. But if there are any questions on k-means clustering and what it means to do clustering, please let me know. There are also other algorithms like support vector machines and principal component analysis that are a bit more advanced. And what they will let you do is they'll take data sets that are in multiple dimensions and then reduce the dimensionality to give you uh, you can ask it to do a 2D representation. So you can ask it to flatten out a multi-dimensional plot. So till now, all the plots I was showing you through that MS Paint example and through the other GIF image, they were all two-dimensional. What happens if you go to 3 dimensions? What happens if your features you have, instead of just square footage, bedrooms, age, you have some other things as well? Then if you try to plot them by hand, it's impossible because we are humans and we can only infer up to 3 dimensions. right? We can only draw things in 3 dimensions at max. So what would happen is if you want to look your data in in 2 dimensions, but it is multidimensional, you can use some of these techniques, principal component analysis, especially to kind of reduce the number of dimensions in your data, and you will get completely different features, which don't really mean anything, but they will give you a plot that you can look at in lesser dimensions. So, well, they would really mean something because they are the principal components, principal axes of your data. So it basically rotates the space in the multiple dimensions and then does projections to get you to lesser dimensions. But yeah, I see a question from Chandri.
Yes, sir. The K-means clustering algorithm is basically the umbrella for the K nearest neighbor classifier. I mean, it's using the technique, but a number of times, updating it.
Well, it's the k-means clustering is different from k nearest neighbors, uh, because k nearest neighbors just looks at the k closest neighbors to it, right? But in this case, this algorithm, it really is trying to analyze the data that you pass to it. It's not trying to predict things, but instead, what it's trying to do is it's trying to look at the data that you've provided, and it's trying to give you some insight. In this case, it's trying to generate clusters and tell you what it thinks, what cluster it thinks that a data point belongs to. It doesn't predict labels, so it doesn't know anything about the labels. It's not a prediction algorithm. It is more of an analysis algorithm. There's more about this distinction between unsupervised learning and supervised learning. Um, we can take a look at this, which kind of tries to explain the exact boundary between unsupervised and supervised learning. So in unsupervised learning, you don't focus on direct predictions. It's instead it's these algorithms are instead geared towards providing you a meaningful representation of your own data and insights about your own data. Let's say you had 100,000 data points, and it was such a huge graph that it was really hard for you to, it might really be hard for you to fathom. It might have a 100 different classes of different data points, might have 100 different classes, but you don't know how to draw circles around each of them. Then this algorithm comes in handy, and then it does it automatically for you. It clusters your data for you. So it can be useful for generating the data, for instance, to then use with k nearest neighbors. So you generate data, you get the clusters, and then you label those clusters yourself. And so now you have labeled data that means something. So it can give you insights, but unsupervised learning algorithms do not predict labels. They only give you insights about your data. That's the main point to take home. Yep, I see a hand from Jamidul.
Yeah, I just want to know that which one is more complex and preferable. Is it a principal component analysis that distributed stochastic neighbor embedding?
I think your audio is cutting off. Okay, I'll circle back to your question. I think the audio cut off, but we can take it up either offline or after this session. We have 20 minutes, so let's move
Okay.
ahead. take a look at some of these other concepts that will kind of form the basis of what you will be trying to do this week. Um, so, yep, the next step here is uh, the thing you enjoy doing the most, which is training supervised machine learning models. We won't spend a lot of time on unsupervised learning because most of our um, days in this bootcamp will probably be spent on training models, fine tuning them, and getting them to give you meaningful predictions, right? Let's get started. So in machine learning, as was mentioned early on, especially specifically for supervised machine learning, um, the algorithms basically are trying to find the most optimal parameters for a model that minimize the error in your prediction. So for instance, in machine learning, basically, as we have discussed so far, you have a function, right? And you're trying to fit that function to the data set. Let's say you have a function like, let me switch to this tab. Okay. So you might have read about, let me enlarge this font. You might have read about quadratic equations in school, right? So what, can anyone tell me what a quadratic equation looks like, or a quadratic function fx looks like? I'll give you a hint.
Ax square plus bx plus c form.
Oh, exactly. Yep, you are right. So we've all learned this at school, right? So this is a quadratic function. And in this case, f is a function of x parameterized by a, b, and c. What does that mean? You get different variations or implementations of f by tweaking your a, your b, and c. In the machine learning world, we call this y, which is the label we are trying to predict. And this becomes a x1 squared. And instead of a, we use the term weights. So it becomes w1 plus w2 w3. So we have three weights, but actually this is a bias. Um, and, and, and these are all different parameters, right, for your machine learning model. So this is a quadratic model. Similarly, speaking of linear equations, and this is where linear regression comes in. Let's look at a linear equation. Can anyone give me an example of a linear equation other than ones who've already spoken? Give you a hint. Okay, I think someone typed it in. Yep, it's correct. Yep, it's basically ax plus b that plots this is the equation for a straight line. If you treat fx as, if you plot it on an xy chart, and you'll get a line. And so if you have a machine learning model that is basically a linear function. And what would your task be? Make a guess. Uh, how would you fit a line to a data set? What would your task be? What would you want to do? Um, it's basically uh, guessing or getting right the parameters. So your task, the task of a machine learning algorithm, an ML algorithm works supervised ML algorithms. Um, it's going to work to get right the parameters A and B. So they try to nail down these parameters using the provided data. What is it that we are able to find out A and B in a fashion such that it fits your data? That's where the magic of gradients comes in. So how many of you guys have read about the concept of gradients of functions? You can just type y or n in the chat so that I can get a guesstimate of if people here are aware of gradients and the level of calculus that you might be familiar with. There's a gradient. Yeah, gradients are similar to tangents. But I see an N from a few people. So I guess I will give you guys, let's see, how can I explain gradients? So essentially, what you are trying to do is in a certain way, you're trying to figure out a method to get to to these uh, these proper values for A and B, right? You're trying to get to the right values for A and B. How are you going to do that? It's pretty simple, really. What you do is you find a way to repeat and get to these points A and B by finding out a thing called a gradient. A gradient is again just like a function of something. You can think of it as a function of something that has a special property. Let me move back to our old and crusty MS Paint. Or wait, I think I might need something else. Let me see if I can find it. I think I found the image. I'm going to drop it into MS Paint and then I'm going to share that screen. Okay. So all right. Stop presenting. Screen share. Share now. All right. So this is an equation of a paraboloid. And I picked this example because it's one in uh, 3 dimensions, right? So you have a function that is it's basically a function of two features. It's x and y, right? Those are your two features, and this is the value or the output of your machine learning model. So in other terms, you can write. Let me increase my font size. Okay. I guess it became too large, but we'll see. Okay. So they're basically saying y is a function of x, the first feature, and x2 um, in a certain way, right? So this is a function in 3 dimensions. And x1 is plotted on the x-axis, x2 is plotted on the y-axis, right? And the y value is plotted on the z-axis. Um, and so you get a function that might look like this if your machine learning model is trying to fit a elliptical paraboloid to your data set. It's very unlikely that you will get a data set like this where you're trying to fit such a paraboloid, but um, essentially what you're trying to do is, um, well, it's not even trying to fit a paraboloid yet. There's a distinction between looking at a gradient and this function is a plot of the loss function and not the actual machine learning model. So let me cross that. This is not, this is incorrect. Oops. All right. So let's assume that somehow you ended up with this kind of an equation for your loss function. What is loss function? I think, oh, well, I guess I missed covering the loss function. Let me see if I can cover the loss function first, and then we'll get back to this paraboloid. Okay. So let's first cover what a loss function is so that you have an idea, and then we'll get into the math part of it. Okay. So assume that you are trying to train a machine learning model, right? What we try to do in machine learning is we try to fit a function like this one, right, that we were looking at by going over examples and computing loss. So go over values of x and resulting documented values of y, right? So you go over values of x and the resulting values of y that were in the data set, that were the actual predictions of y, and calculate your model's loss. So what our goal here is to basically get right the values of A and B, right? We want to get the values of A and B right to make our linear functions equation match what's in a data set. And the data set could be something like, let me open this page. Let's see if I can pull it up. Let's say we are looking at a data set like this one that I'm about to show. Okay. So this is a plot of cricket chirps. So cricket is a kind of an insect, and this is the temperature in Celsius. So, and this is a plot that you can see that you can easily fit a line to this. And then if you get the number of cricket chirps, right? If I fit a line like this one to this data set, and I give it a value of any number of cricket chirps, with a decent accuracy, I can tell you what the temperature in the room is at that moment by just looking at the number of times the cricket, that insect was chirping, right? So this is basically what we are trying. This is our goal. We want to fit a line, and to fit the line, we need to get the slope, right, and the bias both correct. So we need to get these parameters right. But how do we do that? Well, we train it on a list of data that you have. So it might be like the cricket chirps, right? and temperature. So it would be temperature equals A times cricket chirps plus B. And now what you're trying to do is go over each sample and calculate loss. Start with random values for A and B. Okay. So we are going to start with random values. We're going to go over each sample in this space, right? And calculate the loss. Once you have the loss, we sum it up and get an average loss. So there are different ways to calculate the loss. So if you start with random values for A and B, you will get a random line. And for each sample, if I draw a random line, let's say I started with M and B values that gave me a line that goes um, something like this. So let's say I picked A and B values to begin with to start training the model. I pick random A and B values and then ask the model to iterate and find the proper A and B values that are the perfect fit. So what I try to do is I start from the random line might be something like this. If you're able to follow my cursor, it could be a line that goes like this. And so then you will then have to rotate the line and maybe change the bias to kind of fit this line, right? How is it going to do that? So you started with random values for A and B, and now you're trying to go over each sample and calculate loss. There are different ways for calculating loss. Loss tells your model how off its parameters are from the ideal fit, right? How off is my model? So loss tells the model or the algorithm, the training algorithm, right? Loss tells it how off my A and B are. So how off my parameters are from the ideal fit, right? So if you calculate loss, there is an equation for that. It's this one right here. And what it's trying to do, this is called the mean squared error. So what it's going to do is it will look at the difference between the y value that was predicted by your randomly chosen function because you picked random values for A and B, right? So you have a randomly chosen function and you are running the function for different values of x to get all the values of y from your function. And now you have your function's output, which you're comparing with the actual outputs, which was in your data set, and then taking a difference, squaring it, summing it all up, and then dividing it with the number of samples you might have, right? So that gives you your mean squared error. And so how would the equation for loss look like for this sample, this example? Well, it will look something like this, right? So you sum over, I guess I would need a better interface to type stuff in. Let's see if I can format it for it. Okay, so let me try writing it here. All right. So what we are trying to do is we are trying to sum over see if I can actually write things in here. Trying to sum over the loss values. So let's say A times cricket chirps, right? A times cricket chirps plus B. It does not seem to be liking the way I'm typing it in. But I guess you get the point that I'm trying to make. And then I subtract it with the actual temperature. And then I square the whole thing, right? For each item in the summation, I take this difference and square it. And this is, the cricket chirps are coming in from the data set. The actual temperature is also coming in from the data set. So what really is in my control? What can I control here? If cricket chirps is coming in from my data set, so each value for cricket chirps, 1 through n is the number of samples in my data set. Actual temperature is also a column in my data set that I'm reading for each and every item in this list, which I'm looping over. What is A and B? What are these? And uh, no, I did not intend to ask that question. Sorry about that. What I wanted to ask you was, um, what do you think varies, right? What do we have to control here to change the loss value? So this is your loss function at the moment, right? Cricket chirps, actual temperature, both of them are going to be something like this, right? They are going to be each and every single value in your data set. So I want you to think about what actually is being varied here. So if I say my loss is this, right? And I need to square it. I squared the whole thing. Okay. I'll square it. Just assume that this thing is squared. So I have a function, right? It's similar to this over here. I'm trying to, what are the things that are varying here? What are the variables? What can I change to see a change in my loss? If the values for cricket chirps are coming in from my data set, the only thing I can change in this function are my parameters, right? So it's the A and B values, right? So you go over each sample, calculate loss, and then find the next better A and B values. And that is where finding the next better A and B values is where gradient descent comes in. So gradient descent is basically a way, it's a really cool trick that lets you do something like this. So let's say your loss function, the function that represented your loss, see if I can screen share, the paraboloid now comes in handy. So you saw your loss function was cricket chirps squared, cricket chirps minus the actual value squared, right? It was a function of the A and B values, but you'll eventually get a quadratic equation like this one. And what you'll see for your loss function, this would be plot of loss function. This would be a plot of your loss function. And the X and Y axes will be A, and y-axis will be your B parameter. Forget about this part. This will confuse you unnecessarily. This is what your plot function would look like. Conceptually, this is the only thing you need to understand. And you will start with a random value for A and B, right? So if the x-axis is A values, if the y-axis is B values, right? So the y-axis is somewhere here, B values, and this is the x-axis, let's say, A values. Loss is a function of A and B because you're already looping over all your data entry points. And so now you have a function of your parameters. So you will get this, this kind of a plot, right? Now, your goal is to minimize the loss, because the greater the loss, the worse is your fit to the model, right? To the actual function. Okay? So if your loss is high, what does that mean? This one's easy. Can anyone answer this question? What does it mean if your loss is high? And what does it mean if your loss is low? All right, Samilur, you're up. Go ahead, Jamilur. Okay, no worries. Is there anyone else who can guess what does it mean if your loss is greater? Does it mean your A and B values are good? Or does it mean your A and B values are bad? Yep, exactly. Rima got it right. You're correct. Your fit will be worse. It would be bad if the loss is high. It would be good if the loss is low, right? So your loss is a function of your parameters that you are trying to tune or you're trying to get right, correct? So what you're trying to basically do here is adjust A and B to this point right here at this black dot at the bottom, right? You're trying to get your A and B values. You're trying to find the A and B values that will get you to this black dot here because the loss is the least over there. The loss function here is plotted on the z-axis, right? So it's a 3D plot, and your loss value needs to be minimized to get to the best fit, right? So what you're trying to basically do here is to get to this point. Let's say I picked A equals something and B equals something, and I started with this point here. Then let me get better. Yep. So the value for the loss function at this point, A and B, will be somewhere here, right? It will be somewhere here at this. Let me make this larger. Right. It will be at this green dot that I just drew. And I want to go all the way down here. How do I do that? Well, there's this magical property of these multidimensional functions that lets you get to here. You run something known as a gradient on this function and pass in your current values for A and B to get a vector. Is everyone familiar? I guess everyone answered yes to that question when we started this. So everyone knows what a vector is. So what you basically get is a vector in the direction that points to the direction where the function increases the fastest. So in this case, it will point upwards. Let me get a broader. Okay, so it will point like this. The gradient is a vector. You evaluate it at a point, and it's a property of it. It will point to the direction of steepest ascent. And which direction do I need to go if I want to minimize leaks? I know that if I go in the direction of my gradient, I will go in a direction where this function L will be maximized. What do we want to do? Can anyone answer this question? What do we want to do with this loss function? Do we want to, which direction do we want to go? Do we want to go in the direction of greatest ascent, which means the direction where the function value increases the fastest? Or do we want to go in the direction of the steepest descent, which means where it decreases the fastest? So your options are, yep, Mridula guessed it right. Um, we want to go in the direction where this loss function decreases the fastest. So your gradient gives you the direction where it increases the fastest. Now, can anyone tell me, how do I get the direction where it decreases the fastest? I know if I go in the direction of this green arrow I just drew, the function is going to keep on increasing. How do I go in the opposite direction? If I have a vector in 3 dimensions, what do I do? If I have, let's say, p I cap plus q j cap plus r k cap, right? If I have this vector, what would be the direction if this was ascent vector, right? The fastest. What would be the fastest descent? Can anyone type the answer to it in the chat? If this was my direction of fastest ascent, I was increasing my function, my loss value, what would be the direction I'd need to go? What would be the vector I need to use to get the um, direction where the function would decrease in its value the fastest? Okay. Yeah, I'll get the answer. Yep, someone got it. Gradient of vector should be negative. Gradient of vector is really, this is a gradient gives you a vector. You do not take a gradient of a vector. So essentially, you take a gradient of a function like this one, right? And what you do is essentially, then the gradient itself is a value, a vector value, and it points in the direction where it will increase the fastest. So what you will want to do here is just get the reverse of this vector, which would be, you do basically a 180-degree flip, and you would want to get basically this direction, right? You want to go directly opposite to it. You want to go down to this value, right? Because that's where your loss function, which is plotted on z-axis, it's the least, right? So you want to go in this direction. And so that's exactly what we do. We get the gradient and we find the direction where it reduces the fastest. So you take that plus, I need to use a minus because I'm flipping it. I'm doing a 180-degree flip, minus r a cap, right? So this would be my direction for figuring out the fastest descent. So now I know which direction I want to go. I project this vector, which is a 3D vector, to the 2-dimensional space. So I get a direction in 2 dimensions. And finally, what I do is I get the direction I want so I'm projecting this, right? Projecting this orange arrow above gets projected down to 2 dimensions, and it points to the direction which will reduce the loss, right? So I know now where I want to go, given my current A and B values, where I need to go to reduce my loss. I need to go in the direction of this orange arrow, which was projected from this other orange arrow, right? So I finally have my direction of fastest descent to reduce my loss. Now that I have this direction, it's really easy. I can just go ahead and loop over this, right? At every point, I would get the direction in which the loss function is minimized the fastest. I keep picking that direction. I keep updating my A and B values, and I get closer and closer and closer until I reach. So this would be, uh, you saw just two arrows here. The first arrow, here's the second arrow. But this would happen in, let's say, 1,000 steps or epochs, as they call it. So you would do this a number of times because that direction is only valid for a very small relative area of this space. So you can only take small steps and you need to find the gradient over and over again until you reach this point where the loss is the least, right? So now you know how you can reduce the loss and find the values for A and B. And that is exactly how these machine learning models work. They find a loss function. We decide a loss function and ask the machine learning algorithm to find gradients and then drive the parameters in that direction. We start with completely random numbers. We start with completely random A and B values, and we drive down to the place where the loss is the least. There are a few caveats, though, with this method. There are a few pitfalls, and it's not always going to work perfectly, as we will see, but it's how basically gradient descent works. And that's how these machine learning algorithms work. And I see that we are already out of time. So if there's any questions, I'd like to take those. There is material after this in the PDF that I sent on you guys' WhatsApp group. You can check it out. There's a lot more to cover. And we missed out on discussing about TensorFlow and a ton of other stuff. But that's all the cool stuff. I'm sorry we didn't get to it, but I hope this gave you a good overview of what machine learning is about and what really it can do. A lot of people really try to just directly dive into writing code, and there's nothing wrong with it, but it never hurts to kind of know what exactly it's doing under the hood. And that lets you solve problems that someone who just knew how to code does not, because you know the underlying concepts of all this. So here are there's some caveats. There's also a proof in here about how gradient descent works. You can look into all of this after this session. But if you have any questions, I'll be here for the next 10 minutes. Let me know. And of course, I'll also be accessible throughout this boot camp on WhatsApp. Yep, Jamilur.
Yeah. Hello, hello. Am I audible now? Hello.
Yep.
Okay. So back then I asked that in the unsupervised learning, there, as example, you mentioned that the principal component analysis is complex. So there are another thing, it is TSNE. So which one is more preferable and which one is lesser complex?
SVN or SVM?
I am asking about TSNE.
Oh, TSNE. Yep, there is an algorithm,
TSNE.
TSNE. Yeah, so TSNE is also a really good algorithm for dimensionality reduction. I really forgot what exactly it was used for, but I mean, not what exactly it was used for, but why, what's the difference between PCA and TSNE. But both algorithms will give you a flattened, so both algorithms are good at kind of giving you the reduced dimensional values for your features, right? But both of them work in a different way. I'll have to look into it. I did use Disney once for a data set that was about coffee shops. I have a link to that. I'll share it in the chat or on WhatsApp once I find it. But yeah, I guess we can look at Disney.
Okay. No, I was specifically asking about the T-distributed
Yep,
stochastic neighbor
that
embedding one.
yep, that's Disney. Uh,
Yeah.
so I think it yep, it takes, let's see what it does. So, okay. So it computes the probabilities um, for each um, for each object pair. So let's say you have a, a, a gazillion data points, and you have for each data point, what you'll try to do, this is a very computationally taxing algorithm. So it will use up a lot of your compute power because it has to go through each and every single data point and data point pair, and then look at the probability that and calculate a probability value that dictates whether two items are similar or not. And there's some complex math behind it that then finally lets you get to your inferred um, distribution that gives you this um, clustering of different values. So I haven't really followed through the math on this algorithm, uh, but it has to do with Bayesian probabilities, conditional probabilities, and there would be like a deep proof to it. But the way PCA does it is through projections. So this uses probabilities, and PCA uses the the concept of reducing dimensions by doing projections along the main axes. It uses the concept of correlations as well. So this is the main difference. So here it uses probabilities. I guess it would be using counts of things underneath. But yeah, in terms of using it, usually I tried to work on a project that used TSNE and PCA, and we tried both of these algorithms, and we found that TSNE was working better for that data set. And usually you can try running on subsets of your data. You can pick a good trick to figure out which unsupervised algorithm you can pick to use is you should take a random sampling from your data. Let's say you have 100,000 entries in your data set. You pick a random sampling of, say, 1,000 points, right? And then run an algorithm like this one. Then also run an algorithm like PCA, compare the results, and see which one works better for you, right?
Okay. And if I like make it a summarize. So in supervised learning and unsupervised learning, in supervised learning, we are working on the labelable data, and in unsupervised, we are working on unlabelable. And in supervised learning, we are getting the prediction on doing the prediction using the shown structure and pattern and relationship of the data. And in unsupervised, we are main objective here is like finding out the hidden structure and pattern on the relationship of the data. Is it right, or
Yes, that's
there is
absolutely,
something more? Okay.
that's correct.
And the last question that someone just asked in the middle that in finding out the Google Maps. So in the Google Maps, though I know a very little, the main thing I know that in Google Maps they are doing like graph using graph theory, traffic, real time traffic and all data, and geo trafficking and addressing something like that, and also street view. But in some cases, we find out that there are some, but especially in India, like there is uh, no street views allowed. So we found that so many times there's a road, there are a big wall, we can't go further there. So is it possible by using the uh, K mapping or K mean something like that so that we can improve that data? We can make sure that another person not go to the same location or same address, something like that. Is it possible?
So if you want somebody to not go to a point that is not documented correctly, it is more of a software error than something that is a machine learning problem that needs to be solved using machine learning. So it's probably an error in their database, and you could run some unsupervised or even supervised algorithms to figure out if some place is closed or the map is not right. One way to do it would be, let me see if I can pull up, uh, let me see if I can, give me one moment. Okay, so if I can screen share this tab, um, let's see if I can. All right. So this is an example from your city. Um, let's say that you're trying to go to a public vehicles department, and you found that you're trying to get a driver's license, and you went there, but it was closed. Then what Google might be able to do would be look at all these reviews or comments and sift for any comment that might point to it being closed, and then create a kind of a filter that then a human can then look at and say that, yep, this place is closed, it shows open, this should be changed to closed. So that's one example you can use machine learning for, in order to kind of process all of this data in the form of comments. You could use something like BERT. It is a model that lets you get vectors in exchange of sentences. So you pass it a paragraph and it will give you a bunch of numbers, which will correlate with the meaning that is encapsulated by this paragraph. So you now have a vector for each of these comments, and then you run it against a regression, sorry, it should be a classifier here. So you run it against a classifier to see if any post is talking about closure, or if something is closed, or hours. Something, yeah, someone posted here, it's the working hours are 11 to 16. So you will find posts that match in a certain way, in this way. And then you can run some more logic on top of that to kind of figure out if something's closed or not. But it really boils down to how Google manages its data. And you can employ machine learning at some points. But really, what you should be doing is find out the problems first and then try to figure out a solution. So it's not like you have a new hammer called machine learning, and now you're going to hit that hammer on every nail you find. So it's just another tool in your bucket of tools, and you got to find the right time to use this tool to solve a certain specific problem.
Yeah, I got. Thank you.
Hey, um, yep. So yeah, I guess for today, we could not get into all of the fun stuff around TensorFlow and using Colab to write some code examples. But maybe we can get into it at a later session. Uh, I believe I am scheduled for the 29th, to do a session on model deployment. So how do you deploy models once you have prepared them, after training them? How do you get your set of parameters that you tuned using this gradient descent to actually on a platform? But yeah, that's all, folks. And thank you so much for sticking around. It was really a blast to cover this topic with you all. And I hope to see you soon.
Thank you, Aan Patel, sir, for the wonderfully informative session. And everyone, please fill up the feedback form given in the chat box. As we come to the end of day one of the Machine Learning and TensorFlow Bootcamp, we stand before you filled with pride, excitement for all that we've accomplished together over the course of this event. I hope that each one of you have taken something from today's session that will help you in the long not because it's not end. We'll be continuing with the episode 2 on the 19th of July. Till then, keep learning, keep enjoying. Hail Google.
Thank you, everyone. Take care.
Thank you so much, sir.